In this video, we're going to look at how to differentiate parametric equations. So again, this can be done just using the parametrics. So what we don't want to have to do is convert into Cartesian equation. Obviously you can do, but by doing that you might end up with something that's really difficult to differentiate. So again, I would only differentiate the Cartesian if they specifically tell me to work out the Cartesian and use that. Okay, we're going to do everything to do with the parametrics. It says when functions are defined parametrically, you can find the gradient at a given point without converting into Cartesian form. You can use a variation of the chain rule. So it says if x and y are given as functions of a parameter t, then dy by dx is dy by dt divided by dx by dt. Now all that is, that's just come from the chain rule. We know the chain rule, usually we use letter u, dy by du times du by dx. So that's what we know the chain rule as. If I just replace the u with a t, dy by dx will be dy by dt times dt by dx. Okay, if I then flip this second fraction over and say that's dx by dt, then I can say dy by dx is dy by dt divided by dx by dt. And that's just what that is there. It's written slightly differently. So we can, if we've got parametrics in terms of t, we can differentiate each one in terms of t, and then we divide one by the other. Okay, and it's the same if it's theta, dy by dx. If you had them in terms of theta, would be dy by d theta divided by dx by d theta. So you can either memorize it like that, or just remember the chain rule because you already know that, and then so multiply it by the reciprocal. So it depends how you want to memorize it. It's easier just to remember for parametric equations, divide one by the other. Okay, and we can do the same usual things. We can work out where turning points are by setting dy by dx equal to 0. Okay, we will have the gradient function in terms of the parameter, but we can work out where the turning point is at the point. That'll give us a t value, and then we can then go on to use that t value to work out the coordinates in the way that we've done on the previous videos. Okay, so it's all relatively straightforward. Okay, the reason why this will be difficult is because they will give you something potentially difficult to differentiate. So you might have to use the chain rule, you might have to use the quotient rule, you might have to use the product rule, you might have to differentiate trig or log. So the method is the same. They could give you an easy one, where the differentiation is easy, or they could give you a difficult one where the differentiation is difficult. So depending on how many marks they want to award will depend on how difficult the differentiation is. Okay, I can't remember seeing many questions where the differentiation is straightforward. These tend to be the sort of in the latter part of the paper, usually. Find the gradient, example 1, find the gradient at the point P where t equals 2 on the curve given parametrically by those two. Okay, so this is an easy question. Okay, we've got two parametric equations. We want to find the gradient at a point where t equals 2. Okay, so I'm going to say if y equals t squared plus 1, then dy by dt will be 2t. If x equals t cubed plus t, then dx by dt will be 3t squared plus 1. So then we can get dy by dx. So dy by dx is just this one, which is 2t, divided by this one, which is 3t squared plus 1. So we've got our gradient function in terms of the parameter t. So if you need to work out a gradient at a point given parametrically, you need the value of the parameter. So at t equals 2, dy by dx will be 2 times 2 over 3 times 2 squared plus 1, which is 4 over 13. So we know the gradient at the point on the curve given by those parametric equations is 4/13. Okay, let's look at a slightly harder one. Find the equation of the normal at the point P where theta is pi on 6 on the curve given with parametric equations x equals 3 sine theta and y equals 5 cos theta. Okay, so this time we're after the equation of a normal. A normal is a straight line, so we want y minus y1 equals mx minus x1. Okay, so we need to know, we haven't got that. For that, we're going to have to differentiate. We haven't got that, and we haven't got that. Okay, so we haven't, at the moment, we haven't got any information other than the value of the parameter. But we can work it out. Okay, so if we say at theta equals pi on 6, so at theta equals pi on 6, then x equals 3 sine pi on 6. Sine of pi on 6 is a half, so x equals 3 halves. At theta equals pi on 6, y equals 5 cos pi on 6. Cos of pi on 6 is root 3 over 2, so y is 5 root 3 over 2. Okay, so that's just substituting the parameter, value of the parameter into each parametric equation. So we know the x and the y values now. Okay, now we need to know the gradient. So for the gradient, we're going to differentiate. Okay, dy by d theta. If y is 5 cos theta, the derivative of cos is minus sine. So that's going to be minus 5 sine theta. If x equals 3 sine theta, the derivative of sine theta is cos theta. So that's going to be 3 cos theta. So dy by dx is going to be dy by d theta minus 5 sine theta over dx by d theta, which is 3 cos theta. Sine over cos, we can simplify that to minus 5/3 tan theta, or minus 5 tan theta over 3. Okay, this is the gradient function. So we can say when theta equals pi on 6, dy by dx will be negative 5/3 tan of pi on 6. Okay, if you stick that in your calculator, you'll get negative 5 root 3 over 9. Okay, now remember that is the gradient of the tangent. So therefore the gradient of the normal will be the negative reciprocal of that. So it's already negative, so it's going to be positive 9 over 5 root 3, which if you stick that in your calculator, so the calculator rationalises it for you, then you end up with 3 root 3 over 5. And that's the gradient of the normal. Okay, you can stick it in the equation of a line. So y minus y1 is there. 5 root 3 over 2 equals m, which is here. 3 root 3 over 5 times by x minus x1, which is there, 3 halves. Okay, it doesn't say whether we need to get it in the form y equals mx plus c or not. So if it was me, I would just leave it like that. It's perfectly valid. You could rearrange it if you want. You could get the 2 and the 5 off the bottom, but why mess? Okay, let's look at the next question. Find the points of zero gradient. The points of zero gradient. So in other words, dy by dx equals 0 on the curve with parametric equations. Okay. It says you don't need to establish whether they are maximum, minimum or points. So we don't need the second derivative. We just need to know the first derivative. So we need to know what dy by dx is. And we need to solve when that is equal to 0. Okay, so we need dy by dt. And we need dx by dt. Okay, both of those, there's a function of t over a function of t. So for both of these, we're going to have to use the quotient rule. So if I do y first, so I'm going to do y equals t squared over 1 minus t. So I'm going to let u equal t squared, v equals 1 minus t, du by dt equals 2t, dv by dt equals minus 1. So dy by dt will be v du dt, so 2t, 1 minus t, minus u dv dt, so that's minus t squared, so that's going to be plus t squared, over v squared, which is 1 minus t all squared. So I'm just going to tidy the top up. I'm going to leave the bottom factorised. So I've got 2t, and then I've got minus 2t squared, plus t squared is minus t squared, over 1 minus t squared. So that's dy by dt. Now I'm going to need to do the same for x. T over 1 minus t, so I'm going to let u equal t, v equals 1 minus t, du by dt is 1, dv by dt is minus 1. So dx by dt is v du dt, 1 lot of 1 minus t, minus u dv dt, so that's minus t, so minus t is plus t, over v squared, which is 1 minus t squared. So that, tidying up the top, t's cancel, 1 over 1 minus t squared. Okay, so dy by dx is dy by dt. Now I need to divide by that because this is a fraction. Instead of writing that big fraction, this one, all over another fraction, I'm going to say that's the same as multiplying by dt by dx. Otherwise I'll end up with one fraction over another fraction, and then that makes it look more complicated. So I've just multiplied. Dividing by dx by dt is the same as timesing by dt by dx. That cancels out. They're the same, common factor. So dy by dx is simplified to 2t minus t squared. Okay, right, let's not forget what we're doing. We're trying to find the points of zero gradient. So we now know we've got our gradient function in terms of t. We can now find the values of the parameter where the gradient is 0 by solving where 2t minus t squared equals 0. So we're setting our gradient function equal to 0. If I take out a factor, I will get 2 minus t. So there is a turning point when t is 0, and there's a turning point when t is 2. Okay, we just now need to figure out what the actual coordinates are. So when t equals 0, x will equal 0 over 1, which is 0, and y will equal 0 squared over 1, which is 0. So that's the point 0, 0. When t equals 2, x equals 2 over 1 minus 2. So 2 over minus 1 is minus 2. Y will equal 2 squared, which is 4 over 1 minus 2. So 4 over minus 1, which is minus 4. So there's another turning point at the point minus 2, minus 4. Okay, so that question, there was a lot more work. You had to do the quotient rule twice. So that would obviously be worth more marks. Okay, not entirely sure how many, maybe 6, 8 possibly. Okay. Last one, the curve C has parametric equations. The line L1 is a tangent to C and is parallel to the line with equation y equals x plus 1. Find the equation of L1. So the line L1 is a tangent to C and is parallel to that. If the line is a tangent, then we can use the gradient function because that is a function connecting the x value, or the t value in this case, to the gradient of the tangent. If it's parallel to that line, then we know that dy by dx has got the same gradient of that. The gradient of that is 1. Okay, so let's differentiate. So start with the y. If y equals 2t, then dy by dt will be 2. Okay, x, a bit more complicated. We could use the quotient rule, although that might be unnecessarily more complicated. Okay, here we've got one denominator. So what you should be realising you can do is split it. So we can say it's t squared over t, which is t, minus 3t over t is minus 3, and then minus 4 over t is minus 4 over t, or I can write it as minus 4t to the minus 1. So that's just considering 3 different fractions. So split that denominator up. Now we can differentiate it. dx by dt, derivative of t is 1. 1. Derivative of 3 is nothing. Derivative of negative 4t to the minus 1. So the power comes down. Times by minus 4, so that's plus 4. And then we take 1 off the power. Okay, so dx by dt is 1 plus 4 over t squared. Okay, now because we're going to have to divide by dx by dt, it's probably worth making this into one big fraction. So instead of 1 plus 4 over t squared, I can say that's t squared plus 4 over t squared. And the reason why I've just done that is because I know I'm going to have to divide 2 by 1 plus 4 over t squared. It'll be easier if I just have that as one big fraction. So dy by dx is 2. 2. And then I need to divide that by dx by dt. So again, rather than writing 2 over a fraction, I'm going to multiply that by dt by dx. Like that. Okay, so if you dx by dt is a fraction, then multiply, when you're doing dy by dx, write it as multiplied by dt by dx. So that's 2t squared over t squared plus 4. Okay, so let's not forget what we're doing. So we've got our gradient function. There it is in terms of t. The line L1 is a tangent to C and is parallel to the line with equation. So it's parallel to y equals x plus 1, which means that this must have a gradient of 1. So if I say, I'll just rub this out. So if I say 2t squared over t squared plus 4 equals 1. So I've set my gradient function equal to 1, times everything by t squared plus 4. So 2t squared equals 1 lot of t squared plus 1 lot of 4. Okay, and then we just need to solve. So t squared will equal 4, which means t is plus or minus 2. Okay, now it says there, so again, consider the domain of the parameter. T is greater than 0, so I can say therefore t equals 2 because t is greater than 0. So we know we have the parameter equaling 2 when the gradient is 1. Okay, in order to work out the equation of the tangent, y minus y1 equals mx minus x1. Okay, we know that's 1. We know that's happening when t is 2. So we just need to know what the coordinates are when t is 2. And then we can substitute it into the line. So when t equals 2, x will equal 2 squared minus 3 times 2 minus 4 over 2. So 4 take 6 is negative 2, take 4 is negative 6, divided by 2 is negative 3. And y is going to be 2 times 2, which is 4. So y minus y1 equals mx minus x1. So y equals x plus 3 plus the 4, move the 4 over the other side, you get y equals x plus 7. And that's the tangent to the curve. Okay, should now be able to have a practice at the next exercise. There's only one more section to go, and that is integration.